mentioned it is inner product and orthogonality, and inner product is a very good visualization when your basis happens to be an orthonormal basis. That's why inner product is getting very simple representation. Otherwise, if your basis is not orthogonal basis, then inner product it will be defined with respect to some kind of positive definite matrix. So some complex thing would come there, because positive you have in order to define inner product with respect to any non-standard basis, you need to know how to generate that positive definite matrix. So those are a little bit complicated concept. In next module, in next course probability and stat, you may come across to see those kind of things, because in data it doesn't ask that I will have a very specific kind of pattern. Data may be in any pattern, but if you want to apply your method, any kind of optimization algorithm or any kind of algorithm, those algorithms meant for some specific class of problem. So in order to convert that data into a specific class of problem, you need to do some kind of orientation change of orientation. So that's where orthogonality concept will play very important role. It is also very much related with Gaussian distribution and other kind of thing. So linear algebra is coming everywhere, whether it is probability, whether it is a stat, whether it is optimization, whether it is machine learning, data analytics, or whatever it is. Everywhere linear algebra is, whether it is even programming, everywhere linear algebra is coming. So if you are very good in linear algebra, definitely you are very good in other those related concepts. So coming to these are the detail of course, so I would like to skip. So coming to outline of my today's tutorial, first I would like to discuss about the problem from the segment inner product and corresponding orthogonal complement. So here I had already discussed about orthogonal complement. That means if we are having a vector space B, vector subspace B, then we try to find a collection of all the vectors which are orthogonal to V, and that we denote it V per. That means V perp is talking about collection of all the vectors which are orthogonal to every element of the given subspace V. So we write like this way. It is not a good notation. What is the best notation? So or more systematic or algebraic notation, you can say that in V perp all those vector X would be there, whose inner product with any element from the given subspace V is 0. That means inner product or dot product of X with V is 0 for every V coming from subspace capital V. For every V coming from subspace V. So this is this kind of thing we will talk about. So it demands orthogonality concept. Also, it demands inner product, understanding of inner product. That's where I have come across problem to find orthogonal complement of a given subspace. Then I will talk about how to few problems based on construction of orthonormal basis and orthogonal projection. Here directly I will talk about problem. I'm not talking about how it is happening. Those things I had already discussed during theory classes. Then, if time permit, I will go to discuss a few problems from orthogonal transformation. So coming to first part, that inner product and its application in order to find orthogonal complement. So one interesting application is that Pythagoras theorem. You know from your high school what is Pythagoras theorem. That it says that if you are having a right angle triangle, that means a right angle triangle, it is saying that the angle between a smaller side. So what happens? So what are the smaller side? This base and height. This height. Base we used to denote it by B, and height we denote with H. Okay, then angle between this is 90 degree, and consider this one is C, hypotenuse or whatever larger side. Then what is the relation between these length, side length? What are the relation? Relation, it says that C square is, that means a square of the largest side is always equal to sum of a square of a smaller side. Sum of a square, that means B square plus square. Notation can be changed in different book. Notation might be different for side, but here just you understand what I want to say. what message I want to convey. So it is a what theorem? This theorem we are calling it Pythagoras theorem. So how it is related with orthogonal uh, decomposition of a vector into two parts. One is projection part and another one is orthogonal part. So if you consider a line in R3, even in general Rn you can consider, and if you are taking any vector x, three-dimensional vector x, then what can we say about the relationship between the length of the vector x and the projected part of x along the line? So definitely length of vector x, it would be greater than equal to length of the projected part of x is along the line, definitely greater than equal to. So this is the relation I would like to say. This is the relation. You can observe it here. So this is your vector x. You projected into two parts. One, this one is the part along the line. We are calling it x parallel, or we are calling it projection of x along the line. And this part which is perpendicular to the line. So always we observe a right angle scenario. So this, what is the name of this one? We used to call it x perpendicular part. Now, if I'm asking what is the relation between length of x and projection of x along the line. So usually from the picture you can see that always length of projected part would be less than equal to actual length of x. But when equality will hold when x is along the line. If you are taking x is along the line, then equality term will come. So that is the one relation due to this projected part. Now, once we are having this one, we can define Pythagoras theorem. What does it say? We consider two vector x and y from Rn or R3. Here R3 scenario, you can take it R3. Then the equation where it is saying that a square of norm x plus y, it is equal to sum of norm of x and a square of norm of x and norm of y. So this relation we are calling it Pythagoras theorem, and this relation is only when it will hold when x and y are orthogonal. If x, y are not orthogonal, then what will happen? Inequality will come. Inequality, like this kind of things will come. So that means if you are taking any general, like if you are taking any two vector x and y, suppose the angle between those two are not 90 degree, like this way, and then just see the direction. This one is y vector, this one is x vector, and then this vector is what? X plus y. You can call it x plus y. So if I'm asking here, you can observe that the angle between x and y is not 90 degree. It is not a right angle. So here angle is definitely acute angle. This scenario is acute angle. So what relation you will get it here? You will get it here, norm of x plus y. That means sum of these two sides. Then it is always less than equal to norm of x plus, norm of sum of norm of x plus y. Okay. This property we are calling it triangle property, a triangle inequality. But if you, when you observe that the angle between x and y is 90 degree, then it will be reduced to this Pythagoras theorem. So this one is, you can call it triangle inequality in general. If the angle is not 90 degree, then you observe inequality here. But if you somehow you come to know angle is exactly 90 degree between x and y, then what will you will observe? You will observe equality. So this concept, call it triangle inequality. Okay, and when you observe x is perpendicular to y, then this triangle inequality becomes equality. That is the Pythagoras theorem itself. So one more theorem is coming, one more inequality is coming, Cauchy inequality. It is defined with respect to inner product, absolute value of inner product. So if you take any two vector, and here you don't know what is the angle between x and y. Simply you say that the angle is maybe anything. So definitely, so what is the absolute value of this inner product of x and y? It will be bounded above by norm of product of norm of x and norm of y. So this inequality is a very famous inequality. If you want to proof is also very simple. Using the definition of inner product, you can easily establish this proof. I want to go to prove it. So it's a Cauchy inequality is coming everywhere when there is an inequality kind of things, and you need to establish. You need to know what is Cauchy inequality. Don't call it Cauchy theorem. It is actually Cauchy inequality. Cauchy inequality. Here I have already written Cauchy. So few scenario I have already discussed. That means if you are taking inner product, generally it is directly giving the angle between two vectors. So inner product is directly associated with angle between the given two vectors. So what kind of situation we can observe that we consider two vector x and y in Rn, then the angle between x and y, it can be given as cos inverse of this arc cos. It is talking about another way of representing cos inverse. So cos inverse of ratio of inner product with product of corresponding norm of x and y. So this is the definition of finding angle between any two vectors. Just you need to calculate angle. So here you can observe that this is the pictorial view of this representation. How you can find theta. Theta you can find the dot inner product, take ratio and then apply cos inverse. You will get your desired angle. So here consider suppose we are having a population like in one of the example I had already discussed, one of the class I have already discussed about. If you want to find the correlation between two objectives, how can you measure that correlation? You can measure that correlation with the help of inner product as well. So consider two characteristics of a polynomial, like height and weight or something like. Suppose x represent height and weight. Here x is here it is talking about with deviation vectors x and y. That means x and y has been deviated by mean. So initially we had some certain data, then we took mean of that and we deviated it. So x has been replaced by what? X has replaced x minus mu. Y has simply replaced y minus mu. So this mean deviated data. So x, y are mean deviated data. So there is a positive correlation between these two characteristics. That means height and weight. X is suppose x is represent height and y represent weight. If and only if the inner product between x and y is greater than or equal to 0. So just you to check the correlation between two kind of characteristics like height and weight or body mass index and blood pressure, something like that. Any two kind of property you take, and if you want to see measure the correlation, just find the dot product between those two factors. If dot product is positive, then you will say that there is a positive correlation. If the dot product is negative, then we will say that there is a negative correlation. If dot product is 0, then we will say that there is no correlation. So this scenario it is talking about if dot product is acute, angle between two characteristics is acute angle. That means it is saying that dot product is positive. Here dot product is positive. That means it is talking about positive correlation. Okay, and if you say dot product between these two characteristics, height or weight, it is a 0. That means right angle. Then it is talking about there is a 0 correlation. Correlation is what? 0. There is no correlation. Simply we can say that. That means a circular kind of a structure. And if you observe the angle between these two characteristics, that means height and weight is greater than 90 degree, then we of that obtuse scenario, then we say that there is a negative correlation. So this one is significant of negative correlation. So you can measure simply. I would like to say that with the help of inner product, you can measure the correlation between two characteristics of any kind of population or any kind of quantity, whatever it would be, any kind of object. You can measure correlation. One interesting application. Few more I had already discussed. So I told that correlation you can measure with the help of inner product. So what is the best thing through which you can measure correlation? That best thing is Pearson coefficient, or simply you are calling it correlation coefficient. So correlation coefficient also you can define as it is cos theta. Cos theta is what? R, the correlation coefficient. R, it can be defined as a correlation cos theta. So this kind of things when you observe, when you measure correlation with the help of cos theta, then that time we are calling it cosine similarity kind of approach. It is very famous in many machine learning problem. Cosine, you need to measure cosine similarity between two set of vectors. So, so you need to know that. So we know that cosine of this theta, how we express as a ratio of inner product with product of corresponding norm. And this is the scenario of positive correlation. This is the scenario of negative correlation. In positive correlation, what we observe, it is the ideal situation of positive correlation when R equal to 1. And this one is the ideal situation of negative correlation when R equal to -1. So these are different kind of correlation. So further in last example we had already seen that. So but I haven't calculated correlation coefficient. So correlation coefficient you can calculate with the help of this formula. You can calculate because you had already x, you had y, you had so that's why you can easily calculate norm of x and norm of y both. So in that process, the correlation coefficient, if you numerically calculate, then no correlation coefficient was around 0.9782. That means almost perfect correlate, positively perfect correlation. That means perfect positive correlation. What is means? It is talking about when R equal to 1, we are calling it perfect correlation. So here the value of R is coming very near to 1. So that's in the last previous question there was a perfect correlation, almost perfect correlation. And if you are willing to find angle, then angle, how can you find? Just apply cosine of inverse over R, and it is coming around 12 degree. In radian it is 0.21, or in otherwise it is 12 degree. In degree it is 12 degree. So all these are scenario. So the angle between two vectors, I had already mentioned it here. So coming to find it, this one is the actual question of this tutorial. So how to find orthogonal complement of a given subspace. So suppose here question is like that. Consider a vector having a four-dimensional vector having entry 1, 2, 3, 4. Then what we have to find? We have to find the every four-dimensional vector which is orthogonal to this vector. That means in R4 definitely we are having infinitely many vectors because it is a four-dimensional space, and in that infinitely many, among that infinitely many vectors, we have to find those vectors which are orthogonal to this given vector V. So that means this question also we can pose that if you are having a subspace with basis this one basis element, a single basis element V, then we have to find a orthogonal complement of V. That means V per. It would be V per. You have to find V per. So V per, that means it contains every element of R4 which are orthogonal to V. So that is the criteria. So how we can find? Notation is V per. So it is saying that we have to find all four-dimensional vector X which are having dot product with every element of V is equal to 0. So V is directly coming from in the linear span of the given vector V. So this one belongs to V, and it implies that dot product. So we are taking any general vector from dimensional. So technically X will have what? It will have four coordinate, and it is very general kind of element. That means arbitrary kind of element which satisfy that dot product with V is 0. So that means dot product of the given vector 1, 2, 3, 4 is 0. So the X is what? 1, x1, x2, x3. So it is a four-dimensional vector. We need to write in the form of coordinate. So after simplification, what we are getting? We are getting this system of equation. So it is a single system of equation. How can we solve that? So we have to find the solution of space. That solution of space will contain all those vector or R4 in the R4 dimensional vector which are orthogonal to every element, orthogonal to this vector. So we have to find the solution of space. So how can you find the solution of space? So it is very easy to find solution of space because it contains a single single equation. What is it? If you try to look it from system of equation perspective, what you observe. So if you willing to write in the system of equation perspective, how you will visualize this equation, you will observe that first your first column of the coefficient matrix is 1 0 0. Second column of the coefficient matrix is what? 2 0 0 0. And third column of the coefficient matrix is what? 3 0 0 0. And fourth column of the coefficient matrix is 4 0 0. And the unknown vector is what? Unknown vector is x having coordinate x1, x2, x3, x4. So we are writing this one in the system of equation for x3 equal to right hand side vector is what? It is a homogeneous form. So the right hand side is 0 0 0. The right hand side is 0 0 0. So if I'm asking, it is already in reduced form. So there is no need to apply reduced equivalent form. So if I ask in augmented form, what is the basis column, pivot column? So only this one is the pivot column. So x1 is your pivot variable or pivot coordinate, or you can say that dependent coordinate, and others are independent coordinate, or we can call it free variable. So what are the free variable? So here x2 is free variable, x3 variable associated with the third column x3 also is a free variable, and x4 is also free variable. So x2, x3, x4 are free variables. So we need to write express a dependent variable in terms of free variable. So that's where we have written x1 equal to minus 2 times x2 minus 3 times x3 minus 4 times x4, and x2 is free variable, so it would be here x3 is also free variable, x4 is also free variable. So this is giving your solution space of this system of linear equation. If you further simplify, what does it look like? If you take x2 common, you will get this vector. So call it w1. Why? Because v notation we had taken for vector this, and that's why if we are taking any element from v perp, that means orthogonal complement, so we will denote that by w. Okay, in order to just change the identity. Okay, so second, so if you take x2 common, you will get this w1. If you take x3 common, you will get what? W2. And similarly, if you take x4 common, what you will get? You will get w4. So these w1, w3. So w1, w2, and w3, all these are what? These are forming a basis element of v per. So that means you got your v per. So v per will be what? That means orthogonal complement of this v. That means if you are taking any element from this linear span, that would be definitely perpendicular to this vector v. You can verify that. If you find dot product of w with v, w1 with v, what would be dot product? Easily, even I can say without calculation, I can say it would be 0. But you can verify that. So dot product of w1 with v, what it would be? Minus 2 times 1, minus 2, 2 times 1, plus 2. So it would be what? Minus 2 plus 2, and others are 0. That 3 times 0 is 0, 0, and 4 times 0 is 0. So minus 2 plus 2, it is what? Total is 0. Dot product of w1 with v is coming what? 0. So definitely w1 is perpendicular to v2. Similarly, if you are willing to calculate dot product of w2 with the given vector v, then definitely that would be also 0. And if you are willing to calculate dot product of w3 with v, that would be also 0. And in that process, if you take any linear combination of w1, w2, w3, that means you are taking any arbitrary element from the a space v per, then that would be also 0. If you're taking any linear combination of w1, that means alpha 1 times w1 plus alpha 2 times w2 plus alpha 3 times w3. and do dot product with V, then definitely that dot product would be what? 0. Do dot product with V, it would be 0. So that means if you take any, or so this one is any, what does it represent? It represents that it is any general element Y from where? From V per. Because these are this Y is a linear combination of W1 and W2, W3 that form a basis of V per. That's why it is any general element from V per. So, and we are taking any general element and we are finding dot product of that with V happens to be 0. So simply it signify our result. That means every vector from V per is orthogonal to V. So that one is the job to done. Similarly, I would like to solve one more problem. It is also related with orthogonal complement, but it is a little bit different problem. It says that consider we are having now three vectors u1, u2, and u3. So why notation I have taken it u1, u2? These are actually unit vector. Then we have to find a vector. So here u1, u2, u3, all these are four-dimensional vectors. Now we have to find a vector. A vector from R4, that means we have to find a vector, four-dimensional vector, which is orthogonal to all these three. It is just little bit, it is reverse of last question. In last question, we had one vector, and with respect to that, we were willing to find every other vector which are orthogonal to that single vector. Here, it is reverse in sense that we are having three vectors, and we have to find a vector from R4 which is orthogonal to all these given three vectors. So that is the scenario it is here. So again, what we have to find, again process is same. What we do, that means if we consider V as a subspace generated by this given vector u1, u2, u3. That means V is a linear span of u1, u2, u3. Then we have to find a vector which is orthogonal to this u1, u2, u3. It means that we need to find V per. We need to find V per. So again, recall the definition of V per. What does it talk about? It is a collection of all the vector which is perpendicular to every element of V. That means the scenario we are talking about every element of V. That means just try to relate that, try to write that perpendicular orthogonality with respect to basis element. That means if you take any element from V per, that one X, if you are taking any element X from V per, then definitely that X would be orthogonal to U1. Also that X would be orthogonal to U2. Also that X would be orthogonal to U3. And you know that what is the definition of orthogonal with respect to matrix product? We orthogonal inner product of two vector also we represented by like this way. So inner product of X with U1 also we can write it U1 transpose X. That I have several times I have already told that if you are taking two vector X and Y, the inner product also you can define as product of like this way, X transpose Y, projection approach, X transpose Y, this representation. So if you are willing to write this equation, orthogonality equation in term of in this form, then it will take a system of equation form here where the matrix, coefficient matrix will be given by first row will come from U1 transpose, second row will come from U2 transpose, and third row will come from U3 transpose. So you are having a system of equation. Just you need to solve the system of equation. So in the explicit form, it is coming like this way. If you are willing to solve this system of linear equation, so what it will take of this form, that means x1, x2, and x3 would be dependent variable, and only x4 would be independent variable. What you do? You can apply row reduced echelon form or Gaussian elimination method. So this matrix, coefficient matrix, it will take in the reduced form, it will take this kind of form: 1, 0, 0, 0, 1, 0, 0, 0, 1, and last would be some insignificant column would be there. So some non-zero kind of thing, 1, 2, or something would be there. So I'm just putting it dot kind of thing, dot kind. So it is what it is redundant column, you can say that. So that means it is associated with x4. X4 is your free variable, and x1, x2, x3, all those are dependent variable. So with respect to x4, you will represent x1, x2, x3, all these dependent variable with respect to x4. In that process, it is taking solution of space of this system of linear equation is taking this form. That means x1 equal to x4, x3 equal to minus x4, and x3 equal to minus x4, and x4 is itself x4. So if you take x4 common, then v par could be what? It is just a linear combination of the vector 1 minus 1 minus 1 1. So this one is your desired orthogonal complement, what you are willing to find. That means it is a linear span of this single vector. That means v per v, it is a line, and v here, v it is coming as a linear combination of three vectors. So it is a three-dimensional subspace in R4, and v correspondingly v per is a what? It is a line. It is a single dimensional space of R4. So always you can observe the relation that I had already discussed, that if you define a Minkowski sum of v with v per, what would be it would be directly equal to the underline space R4. Minkowski sum of v with v per, it would be equal to R4. So it is you can verify this result as well. So I had discussed this before as well during the class. Now, next part of this tutorial, I will talk about construction process of the orthonormal basis. So here I will deal with indirect question. There, what I will do, I will take few matrices. With respect to that matrices, we know that we can always define four fundamental subspaces. So if we are having a four fundamental subspaces, then it is not necessary that always we will get orthonormal basis for those fundamental subspaces. So whatever basis we will get, we will apply our construction process of orthonormal basis, and we will construct orthonormal basis for all those fundamental subspaces. So that kind of problem will come here in this category. So first question is coming that we have to find a orthonormal basis for the given plane. So if we are having a plane V, we call it subspace V. It is definitely it is a subspace. Why? Because it is passing through origin, and it is a subspace. So x1 plus x2 plus x3 equal to 0. So what kind of it represents a plane passing through origin. And what is the, if I am asking what is the normal of normal vector to this plane? Normal vector you can easily find. That normal vector is what? 1 1 1. For this given plane, normal vector is 1 1 1. But right now we don't need to go with the normal vector. So here our planning is different. Here we have to find orthonormal basis. So we are having plane V, which is given by this equation x1 plus x2 plus x3 equal to 0. Then it implies simply that what is the solution of space. So just write in the solution of space. Again, I would like to say that from this given equation, it is a single equation, but you need to visualize this one as a system of linear equation, and in the matrix form it will take this form 1 0 0 and 1 0 0. So easily why I'm asking to write in this way, because you have to identify which are a free variable and which are dependent variable, and from this representation it is very much clear that x1 is a dependent variable, and but x2 and x3 are free variable. So we need to write express dependent variable in terms of free variable. So that's why we had written x1 equal to minus x2 minus x3, because x2 and x3 are free variable, and x2 is free variable. It would be here x2 itself, and x3 is also free variable. So we have to take out first x2 common. Then what vector we will get? We will get v1. When you take x3 common, what vector you will get? You will get v2. So you can say that this plane is actually spanned by these two vectors v1 and v2. That means this plane is always having two directions. So we got the direction of this plane. But what kind of direction this v1 and v2? What kind of basis element? These basis element definitely are not. Is it orthogonal? So find the dot. So you have to just take the orthogonality. If it is orthogonal, then job is done. There is no need to go for construction of orthogonal basis. Just you need to normalize. But if we are, inner product is not 0, then definitely we will have problem. We need to construct orthonormal basis. So what is the inner product of v1 and v2? So it is minus 1 times minus 1. That means 1. 1 times 0 means 0, and 0 times 1 means 0. That means 1 plus 0 plus 0. So it is a non-zero quantity. So definitely v1 and v2 are not orthogonal to each other. It is not orthogonal to each other. It is not equal to 0. So we have to construct anyhow now construction process will come how to construct orthonormal basis. So construction I had already told that very easy to calculate first unit vector. How you can get it by normalizing V1, that means divide V1 by the norm of V1. Norm of V1 is what? It is just a square root of 2. So you are getting U1. U1 is what? U1 is this vector. Now how can you get another vector U2 which would be perpendicular to U1. So you can get U2 by normalizing V2 per. So first you need to find V2 per. So again notation I have taken wrong notation. It is V2 per. So V2 per is what? So we have already seen decomposition of any given vector in the term of two component. One component is talking about parallel component V2 parallel, that means projection component. Another component is talking about perpendicular component that we are calling it V2 per. So V2 per can be written as V2 minus V2 parallel. So V2 parallel, how we express because V2 parallel it is in the direction of U1. So that's way direction of V2 parallel is already fixed U1, and we just need to find the coefficient. This one is the coefficient. How we can get by taking dot product of U2 with U1. So we are getting this one as well. So we are having U1, we are having V2. So doing all the calculations, we come across to know that V2 per is what? Is this vector. That means first entry is minus negative 1 by 2, second entry is negative 1 by 2, third entry is 1. So how you will get U2? Just by normalizing V2 per. So if you normalize V2 per, that means divide by norm of V2 per. Norm of V2 per would be what? A square root of 3 by 2. So you are getting U2. This one is the unit vector which is orthogonal to U1 as well. So in that process you got the another orthonormal. This is the orthonormal basis. U1 and U2 orthonormal basis. So you had a plane. First you in the first step you calculated your non-standard basis. In the process of finding basis you got a non-standard basis. Then you apply the construction process of orthonormal basis and you come across to see your orthonormal basis of the given plane. So job is done now. Now next I will go to solve next question. Here what I will discuss to find orthonormal basis for kernel subspace of this given matrix. So first we will have to find the kernel subspace of this one. So what is the kernel subspace of this matrix? It is defined. It is talking about defined as it is a collection of all the vectors which is nullified by the given matrix A. That means it is saying that x such that ax equal to 0. So that means we have to solve this system of linear equation. So if you solve, I have already written this one. Actually, this one ax equal to 0. In 0 will be system of linear equation, and this one is the reduced form. How? So apply Jordan elimination method or Gaussian elimination method, or simply you can say that apply row reduce row operation. Row operation, simply elementary row operation, and through that you will get this reduced form. This is the reduced form. From the reduced form, you can realize that the variable x1 and x2 are dependent variable, but x3 and x4 are free variable. X3 and x4 are free variable. So we need to express x1 and x2 in terms of x3 and x4. So that's why we have written. So x1 would be x3 plus 2 times x4, and x2 would be negative times 2 negative 2 times x3 minus minus 3 times x4. So this one is equal to x2, and x3 is already free variable, x4 is also free variable. We need to simplify. In order to simplification, that means we are taking common x3 and x4. So if you take x3 common, you are getting v1. If you are taking x4 common, you are getting v2. So in order to do this, you got the basis element of the kernel space of A. Kernel space of A, you got the basis. So easily you can see that these basis elements are not orthogonal to each other. They are not even orthogonal. So that's orthonormal. So we have to construct orthonormal basis. So how can we construct? Construction process is same. First we normalize V1, then to get U1. Then what we do? We have to find U2 per. Find U2 per. It would be what? V2 minus V2 parallel, and simplify it in order to get V2 per. So this is your V2 per. Now, once you are having V2 perp, normalize V2 perp to get U2. U2 is orthonormal vector which is perpendicular to U1 as well. So you got your desired orthonormal basis. Okay. Anyone is having any question, you can ask. Otherwise, it is already around 45 minutes, so I am going to wind up today's tutorial. Anyone is willing to any question? So here one last question is that this would be exercise number 5. Also you can observe it here. So I am talking it here regarding pure factorization of the matrix. So this is the given matrix. So what you do, first step is that list the column of the given matrix in this form U1 V1 equal to 403. You can easily see that these are not orthonormal columns. So we need to factorize into orthonormal matrix Q and R as a product of orthogonal matrix Q and upper triangle matrix R. So we first process is we need to list the column in the form of vector. So V1 we are calling it first column as a V1, second column as a V2, and third column as a V2. So V3. So first now next step is that construction of orthonormal basis or orthonormal vector. So U1 easily you can get it by normalizing V1. So U1 is this one. This vector is the U1. Next, what you have to do, you have to get U2. In order to get U2, what you have to do, first define V2 per. V2 per is what? V2 minus V2 parallel. V2 parallel is given by in the direction of U1. It is V2 parallel. It is in the direction of U1. U1. So easily you can express that as a scalar product of a scalar time of U1. So you are getting this one after simplification. You come across to know that V2 perp is this vector having entry 21 0 minus 28, and just normalize V2 perp. After normalization, what you are getting U2. Similarly, try to find V3 per what it would be V3 minus projection of V3 in the plane of U1 and U2. So it is, you can say that what is this one? It is in the plane of linear span of U1 and U2. That's way this complete part is what it is. You can call it. It is V3 parallel. That means projection of V3 in the plane constructed by vector first two orthogonal vector U1 and U2. So easily, if you do simplification, you will come to know that actually V3 perp is actually V3 because V3 itself is perpendicular to what V1 and V2. So V1 and U1 and U2 has been constructed from V1 and V2. So in that process, V3 is also perpendicular to U1 and U2. If V3 is perpendicular to U1 and U2, then there is no projection. Projection part of V3 over U1 and U2 is 0. So that's why V3 V3 perpendicular is itself equal to V3, and just normalize it and you get U3. So you are having U3. So what you got everything in this construction process. You can select all the entries of R and Q. I had already discussed. So you will get upper triangle matrix. That means change of basis matrix from the basis any non-standard basis that having basis element V1, V2, V3 to basis orthonormal basis having entry basis element U1, U2, U3. So this is your change of basis matrix from where? From this basis V1, V2, V3 to you are changing your new basis is what? U1 orthogonal basis. That means U1, U2, U3. U3. So you can name it for better representation. You can give a name of these two bases. Call it B and call it A. New basis. So R is a change of basis matrix from B to A. So you got R change of basis matrix R, and also you got Q. Q is what? Is first column is coming from U1, second column is coming from U2, and third column is coming from U3. U3 is the third column. So you got Q and R, and if you do multiplication of Q with R, and result will be what? This matrix. Call this matrix. Suppose if we are calling this matrix M, then Q times R would be equal to M. You can verify this result. Verification it would be. So you have already factored the given matrix M into Q and R. So okay. Any question? Then ask. Otherwise, I'm going to wind up today's